Well, I suppose it's kind of important to talk about, at least for a second here, what a base is. So in a monomial, we have a certain structure, assuming it's a monomial of a single variable. So it doesn't include x and y, it's just an x. You might have something that looks like this. It's in the form of a times x to the b power, where a and b are numbers, just to keep it simple. All right, so an example of that would be something along the lines of 2x to the third power. All right. That x is the base. All right. Sometimes it's not an x, sometimes it's a numerical value, sometimes it's a y, it could be anything. But the idea is that if you have a common base and you're multiplying monomials, then all you have to do is add the exponents. All right. The equivalent relation in an expanded form would be to say if you have something like 3 squared, that's 3 times 3. 3 cubed is 3 times 3 times 3. If I put it all together, if I put it all together, I have a total of 5 3's being multiplied. That's the same as saying 3 to the 5th power. All right, so in the expanded form for the second one, I would multiply 5 by itself a total of 4 times first. And then I'd be multiplying by 5 multiplied by itself twice. But in the grand scheme of things, you're looking at 5 being multiplied by itself a total of 6 times. All right. So instead of actually listing it all out like that, you might just jump to the idea that all I have to do is collect my exponents, and I'll have the simplified form. All right. So then the question would be, well, does that also work if it's related to variables? All right. We know it works with numbers, or it seems to work with numbers. Will it work with variables also? So y cubed is y multiplied by itself 3 times. Then I'm multiplying by another y. So in total, I'm multiplying y by itself 4 times. So it's the same as y to the 4th power. All right. You just got to be careful, because a common misconception would be to say, well, I have 4y, so my answer is 4y. Yeah, it's 4y being multiplied. Now, if it's 4y is being added, then your answer would be 4y, because you'd be adding your coefficients. But here it's different. All right? You're saying y times another y times another y. You're going to be looking at powers rather than sums. All right. In the case of number 4, now we have a leading coefficient, or just the coefficient, because they're not polynomials. So we have to account for those. We would say 2 multiplied by a and a again. Then take that result, multiply it by 3, and then 7 more a's being multiplied. 1, 2, 3, 4, 5, 6, 7. Chuck in some multiplication symbols. All right, so what I can do here is just kind of bounce around. I can multiply my coefficients together, ignoring the variables for a second. 2 times 3, that's just simple multiplication. That's going to give us a 6. Then I would just collect all my a's. I have a total of 9 of them. So a to the 9th power. All right. So the long story short here is that I'm just adding my exponents related to the variable. But it only works if you have a common base. All right. So if this were 2a squared times 3b to the 7th, I couldn't write it as ab to the 9th. That wouldn't make sense. All right. So without doing the expansion, we would want the product of x to the 20th and x to the 40th in exponential form. It's actually not exponential form. It's exponent form. That is a typo, yeah. Let the battle begin. Negatory. 3 per marking period. Yeah. So what's my result? X to the what? To the 60th power. Keep the base, add your exponents. When multiplying monomials with the same base, keep the base as is. So we just write keep the base.
I got it.
Yeah, you see, the thing is, like, you can't always believe the person who says, I got it, because it's the person who is quietly doing it prior to the person who's not quietly doing it that usually gets it in first.
Who actually got it? You. Or did
Keep the base, add the exponents. So when multiplying monomials with the same base, same base, like the bases are the same, as in they're the same base, aka the bases are the same. The bases are equal. The bases are identical. I don't know how else to say it, but I'll say it as many different ways I can think of, but historically that hasn't stopped half the class from screwing it up on the test. So the bases have to be the same in order for this to work. Because I'll see it, it'll happen. This is what I'll get. Somebody's going to do it, and it's not to make fun. This is to become a cautionary tale. So I will see something like x squared times y to the third, and what people will write is xy to the fifth. That is not correct. Also known as wrong. Could even think of that as bad. How do you spell UG? Like in a text, like UGH? Okay. That's.
I spelled Eugene.
Wow, we really buffed up these words this time.
I sure did. I don't know what a dinosaur has to do with anything. So, this is the most common mistake related to this topic, but it is, the answer would be x squared times y cubed.
Oh, so just
Yeah, it's kind of like through addition, where if you have x squared plus x to the third, they're not like terms, so you can't add them. It's the same idea here. You don't have a common base, so you can't add the exponents. All right, so just not a good situation to be in. Now, raising a power to a power. So if I'm taking 2 to the third and raising it to the fourth, that's the same as saying I'm taking 2 to the third, multiplying it by itself a total of 4 times. If you're using the process that we just talked about, keep the base and add the exponents, that would be the same as saying 2 to the 3 plus 3 plus 3 plus 3. So you could get your 2 to the 12 that way, but you could obviously, hopefully anyway, see the drawback to expanding it out. What if it was like 2 to the third to the 70th power? I mean, you don't want to write 2 to the third times 2 to the third 70 times just to add your exponents 70 times. To come up with your result, you need a shortcut. And that shortcut involves you just simply multiplying your exponents. All right? So the first few examples here just have us really kind of proving to ourselves that this technique is going to work. So if I have x to the 4th squared, that's a highlighter. I would have x to the 4th times x to the 4th, which is, keep the base, add the exponents, x to the 4th plus 4, which would give us x to the 8th. Exactly what you would get if you were to multiply the 4 and the 2. All right. But then we could throw in a little wrinkle here. We throw in a new variable, x squared y cubed. All right. So x squared y cubed, so 3 times, x squared y, x squared y. So what we'd have to do here is keep the base, add the exponents for the x's, x to the 2 plus 2 plus 2, and then do the same thing for the y's, so times y to the 1 plus 1 plus 1. All right, there's an understood power of y, power of 1 for each of these y's. All right, so a standalone y is really y to the 1st power. All right. So that's my license to say 1 plus 1 plus 1. So I'd be looking at x to the 6th power, y to the 3rd power.
Why do you keep the bases the same?
Say it again?
Isn't y part of the base?
They're 2 separate bases within the monomial. So you can move things around. The property that allows us to do this goes right back to Unit 1. Let me just rewrite it. I'm going to move some stuff here. I'm going to rewrite this as x squared times x squared times x squared times y to the 1st times y to the 1st times y to the 1st. What property allowed me to do that? It was a property of multiplication that tells us that it doesn't matter what order you multiply in, you're still going to get the same result. Commutative. Awesome. So commutative property of multiplication tells us that I can move some things around. So now I could write it as x to the 2 plus 2 plus 2 times y to the 1 plus 1 plus 1. And that bridges us to the final answer. All right. So do we want to have to write stuff in a different order in order to come up with that relation? No. You just pick and choose the pieces of the product that you need. Yeah. All right. So then 2x to the 3rd raised to the 5th. So that's 2x to the 3rd times 2x to the 3rd, 2x to the 3rd. That's 3 of them. I need 2 more. 2x to the 3rd, 2x to the 3rd. All right. So each of those 2's can be thought of as 2 to the 1st power. I mean, you could just multiply all the 2's, just grab your calculator, multiply all your 2's. But the issue becomes, well, what if it's not a 2? What if they're pi's? And you want to express your answer as a power of pi, or even just some not so nice value. Or, worst case scenario, you come up with 32 when you multiply these things, but that's not a choice. You know, so what do? This is the technique. So we're going to add our exponents, 2 to the 5th power. And again, the question is asking for exponent form, so that's another thing. 2 to the 5th, x to the, if I add up all those exponents, what do I get? X to the 15th. All right, so then the last one there, negative 2a cubed b to the 4th times negative 2a cubed b to the 4th times negative 2a cubed b to the 4th. So in exponent form, negative 2 cubed, a to the 9th, b to the 12th. All right. So what's going to be the result of x squared to the 40th? X to the 80th. All right, so when raising a power to a power, you multiply the exponents.